All right, let's go over it. Let's see how y'all did. It looks like some of y'all have gotten the right answer, which is fantastic. 32,653 miles per hour, right? Very, very reasonable, very feasible. That's right. That's right. Okay. So again, we're going to quiz tomorrow. It'll be either one like this or the one where it's flipped around like we did in the notes on Friday. Well, the other one is just like this but different, right? This backwards. Yep. Okay. So let me choose. I'll choose. How about blue? Okay. So remember, we said in this case you don't necessarily want to use the formula V equals R omega because, as I said in class the other day, you end up with like compound units, like I forgot what I said. Let's just see what I said. Like miles per inches hour, right? And then you're going to have to convert it. So although you could do it that way, I have found historically, and by history I mean last 20 years, in my experience, that it's just easier if you do it stoichiometrically. Okay. So let's go ahead and start with the two numbers that are given. One of those, if you imagine driving, we have control over, right? And that's the which one? When you're driving, can you like press a button and have your like radius of your tires get bigger? Maybe, right? Maybe, but more than likely not. If you just kind of hit the accelerator, your car will speed up and slow down, causing your tires to spin faster or more slowly. So you start with the independent variable, the variable quantity, which is 368. So 368. And then RPMs, remember, is revolutions or rotations per, and then you can put 1 minute. Revolutions, rotations, whatever you want per minute. Okay, so now we need to get to miles per hour. Miles per hour. So the first thing that you might say, oh, how do you get from revolutions to miles? Well, I'm not sure. But from minutes to hours, I can handle that one. So let's do that one first. So you can put a dot, or you can put a time sign, or you can put parentheses. Oop, that's not a good horizontal line. There we go. So then minutes is up there, and we want miles per hour. So we put hours down there where we want it, and then you just ask yourself, do we know that conversion factor? We should. How many minutes in an hour? 60 minutes in 1 hour. And then you can see for yourself, minutes divide out. Okay, so now we're left with revolutions per hour. So we got the hours set. Boom. Now we need to get rid of revolutions. So one revolution, down here, one revolution, if you put 2 pi radians, is that wrong? No, it's not wrong, but it's an unnecessary step because it doesn't quite get you where you want to go. The magical step is the one that takes you from rotational motion to linear motion. And that's the one that we did on Friday with an asterisk above it. One revolution of any tire is going to transfer the car down the road by the exact length of the what of the tire? The circumference. Okay, so the circumference formula is 2 pi r. You do need to have that memorized. That's one of those ones I'm not going to give you. And so let's go ahead and say then that 2 pi r is when the radius is 15. 15 times 2 is 30. So that's 30 pi inches, right? Or pi d, right? 2 pi r or pi d. And again, it's kind of fun to do this. So divide them out. And now you take inventory. We have inches per hour. They're like, oh, okay. That's a measure of speed or velocity. So good so far. So far, so good. But we want miles per hour. So now we need to go from get rid of inches and end up eventually with miles. So inches needs to divide out. We'll put it there. And I'll put miles up there. Do we know that conversion? Miles per an inch or inches per miles? No. But I do know that I can go through the middleman of feet, right? So 1 foot is 12 inches. And then again, your inches divide out. And now we have feet per hour. And we're getting closer and closer. So now we just convert from feet to miles. And this is the one we should know. If you don't know it, memorize it. 1 mile is 5,280, 5,280 feet. And then one last time, your feet divide out, and you take inventory of your resulting units, and you have miles in the top and hours in the bottom. That's miles per hour. Life is good, right? Life is good, unless you're a Saints fan, right? or a Chiefs fan, right? Otherwise, life is good. Okay, so now it's just a matter of typing it all in correctly. Typing it all in correctly. So remember, any number that's a factor in the bottom, just go divided by. There's no like 2 pi parentheses we need to worry about in this case because the 30 pi is in the top. So here we go, 368. We don't have to worry about the ones, right, because they're the identity element of multiplication. Times 30 pi, and then pi, you don't need to put times. You could just put it after the 30, and that implies multiplication. Divided by 12. I did. Yeah, good. Let's just leave it like that for a second. Okay? And I hit enter, and I'm like, oh, yeah, there you go. I'm going to write that down. 22080. So the car is traveling down the road at 22,080 miles per hour. All right? Now, if you're driving through Land Park at that speed, are you going to get a ticket? If they can catch you. I don't think they're going to. Yeah. So, yeah, you either drive 20 through Land Park or 22,000. Either way, you're good. Now, that's an unreasonable answer, so we did something wrong, so I'm going to come back. I know my setup was right. I thought through that. So it's just my input here. I did hit the plus sign instead of the multiplication sign. So there it is. And now I get 32. That makes a lot more sense. So 32.843, right? Or 32.844. Either one of those, 3 decimals, round or truncate. And then what are the units on the end? Miles per hour. So you can either say MIL per HR, that's fine, or you can stylize it MPH. Either way, okay? Now, it wouldn't be cool to have like a digital speedometer in your car that is that accurate? Right, so like you're driving through Land Park at 20.001 MPH, and the cop pulls you over, and he's like, I'm going to ticket you. You're like, what? You're like, you're speeding. Slow it down there, partner. Where's the fire, right? Yeah. Now, I did talk to the police chief's son, right? Some of y'all may know him, Ben. And he said that his dad, unless you're going 15 miles over the speed limit, he's not going to even bother with you. 15! Not 5. 5 is kind of like what most people are like, I can fudge 5, right? But he said his dad, police chief, 15, okay? Right? So, wow. Right. So you're going 85 and a 70, and you wave at the police chief as you go by, and he's like, keep it mathy, right? That's crazy. I'm not going to give any last names because people watching the video, I don't want to get the police chief's fired. But he can do what he wants to do. He's the police chief. But you know what? Yeah. Okay. Anyway, yeah, I'm recording. So anyway, now if it's me coming home through Land Park, pulling off of San Antonio Street right there by the front of Worcester across from KC Hall, taking my girlfriend, who is now my wife, home at 1 o'clock in the morning, as I'm slowing down from 35 miles per hour to 20, and he's parked, right, here's the KC Hall. Here is the Worst Fest grounds, right? Here's the underpass that you come under. You come like this, and it keeps going straight, and then you turn right there, right? There's that first little turnout to go into the Worst Fest, and then you come down here, and then there's the mini golf, right? Okay, so I'm coming around the corner, 35 miles per hour, 1 o'clock in the morning. My wife lives at the top of California on Texas Avenue, so I'm taking her home. Her dad's waiting for me, so I'm trying to get there, expediently, but without speeding. So 35. I'm slowing down towards 20 because I travel that route all the time to take her home, and I'm driving right through here, and I maybe hit 20 miles per hour right here. The cop, Officer Ives, if you're still listening, right? He's sitting right there, and it's pitch black, and he catches me going. How fast do you think? 28 miles per hour. I'm slowing down. I'm on the process of slowing down. He catches me going 28 miles per hour at 1 a.m. in the morning. I shouldn't have been out at 1 a.m. I guess I shouldn't. That's my fault, but we were having fun. So anyway, 28 miles per hour, he tickets me. And that was unfortunate. So just be careful. I mean, I what could I say? I sit next to your daughter in street law. Officer Ives. She's a great student. I let her copy off me all the time. In Miss Kingsbury's class, by the way, Cliff's mother. It was a great class. Yeah. I sit next to your daughter, Officer Ives. Can you just get me a break? He's like, have a great evening. I mean, he's real polite about it, right? He's just like, whatever. So anyway, he caught the town miscreant that night. I was on my way to go terrorize the town and start some fires, and he caught me. He caught me red-handed. So this is all hypothetical, right? By the way. So just whatever. If that were the police chief, though, he would have been like, whatever, right? And then I was, of course, late getting my girlfriend home, and so I had to talk to her dad, who was good friends with Officer Ives, and he just laughed and laughed and laughed, and he said, "You're not going to last, boy." And I ended up marrying his daughter. So anyway, it's a happy ending. It turns out all right, hypothetically all speaking, right? So anyway, if we do this on a quiz tomorrow, y'all can handle it, right? Yeah, you can handle it. You set it up one time, make sure your unit's right, and then you all type it in. Now remember, if that 30 pi had been in the bottom, I can't emphasize this enough. In this problem, it would have been wrong, right? But we work the other way. You have to divide by 30 and then divide by pi, or you divide by the quantity 30 pi in parentheses, right? Okay, make sure you do that. All right. Yeah, you're going to get an unreasonable answer if you do that. Now, in miles per hour, we can spot that, but if you get RPMs, you may not recognize it as an unreasonable answer, okay? Whereas, 100, 200 miles an hour, you can recognize as unreasonable. Okay, so let's move on. Let's finish the notes. Example 9. Hold on to your homework. I know what you're saying. What's homework? What's that word? Yeah. What is homework? Okay. It's the stuff that you're doing, right? Worksheets. Make sure you're still doing them. And I'll talk about the calculator thing at the end of class. Okay, remind me. Because if you don't have one at home, I'll show you how you can do it. All right. Approximate. Part A. Approximate the linear speed of the Earth. Y'all ever heard of it? I guess Earth should be capitalized, right? I don't know. Maybe not? Okay. Hey, speaking of Earth, did y'all see the moon the other night? Yeah, the wolf blood moon hound super. Yeah, it was pretty cool. Like around 10:41, it was total eclipse, and then after that, it went orange. It was pretty neat. It's orbiting the sun. Approximate the linear speed of the Earth as it goes around the sun. Assume that the orbit of the Earth around the sun is nearly a circle with a radius of 93 million miles. That's another good thing to kind of know. How far away are we from the sun? Approximately 93 million miles. Okay. Now, the Earth does not really travel around the sun in a circular path. It's elliptical path. But the eccentricity, which is a measure of roundness, is really, really, really close to zero, which means it's really, really close to circular. So it's still elliptical, but it's almost round. So we're going to assume that it's round. So the average distance from the sun is 93 million miles. Okay, that's a long way, right? So here's what we want to do. This is kind of like the coolest ride at the Comal County Fair. Have you ever ridden what used to be called the Sizzler? No? Okay. The Sizzler was cool. It didn't do any flips or anything, but it had an axis here that rotated, and you were in a car. These were arms that had cars attached to them, right? And the whole thing spun like this, okay? Now, in the car, let's say the Earth is the cars themselves rotated. Oh, they call it the orbiter now? Yeah. But it doesn't go up or down. This one stayed flat. Maybe now they kind of go up and down along different planes. But it's cool. It's kind of like riding the teacups at Disney World a little bit. If you kind of hit it right, you can feel that G as you just hit the corner just right. When you get the combination of both spin effects, you're like, whoa, right? Let's ride them teacups again. Okay? All right. Anyway, Earth around the sun is kind of like, I just lost this. Earth around the sun is kind of like the Sizzler ride or the teacup ride, either one. And I don't know if you feel it or not, but it's happening, right? Now, it's happening on such a grand scale that you probably don't feel it. Now, if you go outside on a windy day, you're like, ooh, it's windy today. Is that because you're feeling the wind of the Earth moving around the sun? Like it is when you stick your head out the window of a car? Be careful when you do that. All right, so let's go ahead. Does anyone happen to know how fast the Earth is moving around the sun? Thousands and thousands of miles? Pretty fast. There you go. Right? If we roll down that window, which I wish we could, and you stick your arm out, like in a car, you could feel it, right? That's not the wind, but we're moving. So, okay, let's figure it out. So here's what we're going to do. We're going to assume that the sun is sitting at the center. It's really sitting at what's called a foci. And there's two foci in an ellipse, and they're really, really close together. So we're going to assume that there's just one. Okay? This is 93 million miles. We want to figure out the linear velocity that the Earth is traveling around the circular path. We also call that the tangential velocity, right? So as the Earth is going around the sun, if it were to break out of its orbit in a tangential velocity, how fast would it be careening towards our doom? Right? It's the same question. All right. So what formula are we going to take? We're going to take V equals R omega. V is linear velocity. We're going to measure it in miles per hour. R is the radius, and omega is the angular velocity. So let's just go ahead and plug in. The radius is 93 million, so that's 1, 2, 3, 1, 2, 3. Like you're polka dancing. That's how you know how many zeros you get. Just do it twice. 93 miles over 1, if you want, okay, times the angular velocity. Let's read. Did it give hold on to your homework? Is it? Okay. I'm stuck. Can anyone help me? I need to know something about the angular velocity of the Earth around the sun. Well, let's see. Let's see if our science class in our youth pays off. The Earth makes one rotation around the sun every 57 degrees Fahrenheit. I'm just guessing. Every year. Thank you. No, that's good. That's good. Every 1 year. That's great. Good. So now we have rotations per time. We want miles per hour, right? So we need to convert from years to hours. Now, we could save ourselves a conversion if we replace 1 year with what? 365. So if you did not do that, if you just called it 1 year, then you would have the very next conversion would be 1 year over 365 days. Now, you could use 365 or 365.25. It matters really not. We're just getting an approximation. Okay, so does anything divide out right now? Now? No, we have units of miles rotations per day. So there's a few more computations we need to do. We do need to get miles per hour, so we do have miles correct. That's great. Let's work on days, yeah? Let's get from days to hours. 1 day is how many hours? Too many. 24. Yeah, very good. Yeah, 24 hours. So days divide out. Is that right now? Miles per hour? Dang, that's it, miles per hour. So we just type it in now and we have it? Nope. What's still there units-wise? Rotations. Those are units. So if we get multiply right now, we're going to get units of miles rotations per hour. If we reported that, the Martians are going to laugh at us. Okay? That's not a unit of speed. Right? That's how they talk, I guess, like robots. So we need to get rid of rotations and replace it with something else that measures rotation, bless you, that is unitless. Rads. Cool. So I need rotations to divide out. So one rotation is how many rads? 2 pi rads. I'll put rads there. Rotations divide out. And now rads are unitless. So now I have miles per hour. That's good. All we got to do now is type it in. All right, let's type it in. Typing it in. Scoot this fella over. Over there, fella. All right. Now we flush. Okay. 93 million. 93. And here we go. Let's polka. 1, 2, 3. 1, 2, 3. Or you can waltz if you want to go slower. 93 million. And then divided by 365. Divided by 24. Times 2 pi. Times 2 pi. Big bucks, no whammies. Hey, whoa, 66705.049 mph. Wow, that is exactly what Noah said it was going to be. A lot, right? We are traveling around the sun at close to 67,000 miles per hour, 67 kmph. That's kind of good to know, right? Just bring that up with your friends. Like next time you're outside walking and you feel the wind, you're like, ooh, there it is. We're traveling around the sun at 67,000 miles per hour. You feel it? I'm like, you're weird, right? I'm like, yes, I'm a walking encyclopedia. Okay, and then they're going to ask you something you're not going to know the answer to. Yeah, phone a friend, right? Wikipedia, Google. But that's only part of the fun that we have on planet Earth as we go around the sun, because we are also, as I mentioned, rotating on our own axis, right? Spinning, spinning, spinning. So if the radius of the Earth is about 3960 miles, that's another good thing to kind of know. And of course, the Earth is not a perfect circle, right? Nor is it a perfect flat. Yeah, flat earthers are lost at this point. They're like, what? Isn't Earth just like a sheet of paper, like a magic carpet, flat magic, we're traveling around the sun, right? Nope. What's a radius, right? What is the linear velocity of a math student around the Earth's axis if he's vacationing in Ecuador? Okay, so the 3960 is approximately the radius of the Earth measured at the equator. Okay, so there you go. So let's go ahead and figure that out. V equals R omega. So now the radius of the Earth is about 3960 miles. And again, you can put that over 1 if you'd like. We want to end up with miles per hour. So now I need to get something involving the angular velocity of planet Earth. Planet Earth. One rotation every 24 hours. There you go. So we have miles per hour already, don't we? But we still have what to get rid of? Rotation. So a real quick conversion, one rotation is 2 pi rads. And now rotations are gone. You could also have said 2 pi radians over 24 hours. You could have gone straight to that. But right now we're left with miles per hour. And so we could type this in. And there it is. 3960 divided by 24 times 2 pi. Oh, it depends what units we're trying to get to. We had to introduce the circumference for a rotation because we didn't have units of length already in the problem. We just had revolutions per hour. So we needed to get from revolutions to inches or feet. Okay? But in this problem, we were given the radius in miles, which is already a unit length. So we just needed to get the conversion gone. Okay? So we just multiply. So again, the quick answer to your question is if you analyze the dimension or the units to get what you need, you'll understand if you need to multiply by one rotation is 2 pi r feet, inches, miles, or one rotation is just 2 pi radians. Yeah. Yeah, so notice if I did multiply by one rotation or the conversion factor one rotation and I gave the circumference of the Earth, now if I multiplied, I'd have miles squared per hour, right? Miles times miles for the circumference per hour, and that wouldn't really work. Okay, so there it is. 1036.725 or 6 mph. So that would be the tangential velocity, not if the Earth went out of its orbit, but as the Earth is spinning, if you were to somehow leave the ground, you would fly off the face of the Earth at 1,000 miles per hour. Okay? Right? So that double G, like when you're spinning here, and like if you're catching it over here, like let's say you're approaching this place where it turns around, and then you're right here. You're right there as this thing is spinning in that direction. You're going to feel the combined effect of this G-force and this G-force right at that same moment. You're going to basically be feeling 66,705 plus 1036. So you're going to be feeling closer to 68,000 miles per hour, right? But of course, these are such huge numbers that, and the Earth is so huge, and the solar system is so huge and the galaxy is so huge that we don't really feel these, on a local. Oh, there you go. We do. We're just used to them, right? And that's why we use hair gel when we go outside, because we don't want, at these speeds, our hair to blow away, right, or fly. It messes our hairdo up, right? Yeah, this is a recipe for a bad hair day, right? Yeah, I don't know if we really feel them, but when we shrink it down to a smaller scale, like when we make the Sizzler or the Orbiter, now we can feel it, right? Now we can feel it. Yeah, so golly, I was thinking about, we can add it to this problem. On planet Earth, if you install the Sizzler that is rotating on planet Earth, you can actually get some more combined effects. But it's not going to be much, because we would just be adding maybe somewhere down here in the tens of miles per hour. Okay, but anyway, there you go. Good to know. The Earth is traveling through space at about 67,000 miles per hour, while we are spinning at about 1,000 miles per hour. Right. Yeah. I mean, if you take into the Milky Way spinning, if you zoom out here, right? If you think of, like, here's planet Earth, right? Everything is spinning. There's Earth, right? But I mean, really, if you zoom out to the Milky Way galaxy, that's spinning. Does it work? Yeah. Oh, it's not letting me do that. There we go. Go out to the Milky Way galaxy. Right. Right, and now it's just like, there's the significance of our existence. Right. Happy Monday motivation on a Tuesday. I know. I was getting there. I was getting there. Okay. All right. Man, why should I do my math homework now? Right? No. Right, because we don't live like that. We live locally, right? We live locally. We don't live globally like that. And by globally, I don't mean like concern for other people on Earth. I mean like universally, like Galaxian. We don't live Galaxian, right? We live locally. So it has meaning locally.